Bom dia a todos. Meu nome é Alberto Shimahara, sou um dos engenheiros de aplicação da OPENCADD. Mais uma vez, hoje vamos fugir da rotina. Normalmente, nossos webinars acontecem às quintas-feiras, mas hoje teremos uma terça especial. Trazemos como palestrante um convidado, engenheiro de aplicação da MathWorks, Naveen Bonagiri. Trabalha no escritório da MathWorks em Novi, Estados Unidos, há pouco menos de 2 anos. Possui larga experiência na indústria automotiva. Naveen é especialista em sistemas embarcados e sistemas operacionais de tempo real. O tema de hoje é ADAS e direção automatizada com MATLAB Simulink. A apresentação será feita em inglês, mas vocês podem fazer perguntas em português caso sintam-se mais à vontade, né? Pois eu estarei aqui intermediando esse questionamento entre vocês e o Naveen. Se vocês quiserem enviar em português mesmo pelo chat, eu farei a tradução e poderemos colocar uma discussão com o Naveen. Beleza? Bom dia, novamente obrigado pelo tempo de vocês. Naveen, now is your show.
Sure, yeah. Thank you for introducing me. Hi, everyone. I am Naveen Bonagiri. As Alberto said, I'm part of the application engineering team for ADAS and automated driving at MathWorks office in Novi, Michigan. I work with our ADAS and automated driving customers, more specifically on coder products to help them adapt MathWorks solutions. Welcome you all to today's presentation on overview of our tools for ADAS and automated driving. This presentation mainly has 4 sections. First section is going to be introduction to our tools, and then next 3 sections are going to go into individual sections a little more closely and talk about capabilities of those areas. There is a time for questions at the end of the presentation, and we have other team members from our company to support with the question session. And also feel free to send your questions through chat as well. We can answer them through chat also. And also there is four poll questions which are posted in the webinar in between. If you can help answer those questions, that will help us some of our investments driven into those areas which is of your preference in the future. With that, let's get into presentation here. There are several trends that are driving MathWorks investments in this area. The first is the need for virtual worlds. The industry continues to do more with simulation in order to reduce vehicle testing as well as explore scenarios that may be difficult or unsafe to do in the real world. MathWorks provides tools that allow you to design and simulate scenes, scenarios, sensors, and vehicle dynamics. The second trend that is driving MathWorks investments is the need for multidisciplinary skills. Developing an automated driving application requires variety of skills from planning and controls to perception disciplines like detection, localization, tracking, and sensor fusion. MathWorks provides dedicated toolboxes to help you learn and apply these disciplines. These toolboxes, metrics, and analysis capabilities you can use throughout your development process. The third trend that is driving our investments is the need for software. Our investments here are focused on strengthening our platform tools to enable you design, deploy, and test on the embedded software. Test the embedded software. To illustrate how these different investments come together, let's take a look at some of the examples that we ship with each release. Let's say you're developing a highway lane following application. You would have components for perception, tracking, decision, and controls. In order to design and test these systems, you will likely want a virtual environment that allows you to generate the camera images, radar detections, and also model vehicle dynamics. And after that, you wanted to assess overall system performance. This is an example that we have been shipping for few releases. Each release we incrementally improve upon it. This example here helps you learn how to architect and simulate at the system level. We now also ship examples that help you design each of these different algorithms in each of these different disciplines. We have examples that show how you can get started at the algorithm level. You can also use the simulation environment to help you gain confidence in algorithms you design. And you can learn how to algorithm. Once you have code for this algorithm, you get the code from MathWork, or let's say you had some uncoded the code yourself. You can bring that code back into the system level simulation and gain confidence that the code is functionally correct at the system level. In addition to running interactive simulations, MathWorks provides tools that help you manage tests and report results. You can automate the testing at your desktop or on a cluster or on the cloud. And also you can reproduce all the examples that are shown here in this presentation, but we have customers that extend these examples or workflows further in their development process. You can bring that generated code back into the system level simulation and gain confidence that the code is functionally correct at the system level. In addition to running interactive simulations, MathWorks provides tools that help you manage tests and report results. You can automate the testing at your desktop. One area where we see a lot of interest is in creating scenario variations. Once users learn how to create virtual scenarios, they start creating variations and use simulations to help them identify new scenarios of interest to add to their regression tests. We also work with our customers to help them identify new scenarios from their recorded data. We help them extract information from their CAN log or directly from camera or LiDAR data. Extracting information directly from camera or LiDAR data often begins with a labeling process. From the recorded data and labeled data, we help them identify scenarios of interest and help them recreate simulations of the recorded data. They can then integrate those into their design and testing workflows as well. The examples that I talked about demonstrate some ways that customers develop automated driving applications with tools from MathWorks. Now that you have a scene for, now you have a understanding of how these tools can come together, we'll take a closer look at some of the newest features and examples that align with the areas of investments for virtual worlds, multidisciplinary skills, software applications. This is the end of introduction sections, and it's a time for the poll question number 1. Alberto or Sylvia can post the first poll question here.
Pessoal, vocês podem votar, né, quais são a maioria dos cenários que vocês têm interesse em simular. Se seriam rodovia, estacionamento, ambiente off-road, tá? Fica à vontade para a gente ter uma ideia do qual é o desafio de vocês para a simulação de cenário.
Okay, moving on to the next section here. In this section, I will cover MathWorks investments that are in the virtual world area. In this virtual world, we'll cover scenes, scenarios, and different sensor modeling capabilities. Last year, MathWorks introduced a tool called Roadrunner. Roadrunner is an editor for designing 3D static road networks that can be used in automated driving simulations. Roadrunner can import a variety of formats. It has a graphical editor for you to edit the scenes and can then export into formats that can be used with most of the popular simulators available in the market, like Carla, CarMaker, NVIDIA Drive Sim, to name a few. And you can see the list here more. If you haven't seen Roadrunner before, this will present some portions of the tool to show how it looks like. As you can see here in the video here, it's easy to edit roads and update the road lane characteristics. And also you can add roadside objects and also like roadside objects like traffic drums. And you can also add road signs. And also you can add traffic lights, and you can simulate intersections as well. You can program the intersections accordingly. Here I'm going to show workflow of exporting the Roadrunner scene to Carla. First, to export it to Carla, you begin with a scene in Roadrunner, and then as you see, I made a few changes here to edit the road. After that, I'm changing some road materials, and then also adding some road markings here. After that, you can export the scene into export the mesh into Roadrunner and import into Carla to simulate the same. Here you're seeing the exporting options here. Here we are exporting into FBX format, and then once you have exported, you can import that into Carla. As you can see, it's very quick process of to import the mesh into the Carla, and once you import it into Carla, you can simulate the scene in Carla, as you can see here. Once you import the scene into Carla simulator, if needed, you can visualize it for the semantic segmentation. After that, you can also add required actors as it's shown here, and then you can simulate the scene as well as actors in Carla. In 20A, we provided an addition to Roadrunner called Roadrunner Asset Library, which is a set of 3D models and assets for scenes you want to create with Roadrunner. The library provides hundreds of assets, including road and highway signs, traffic signals, road surface markings, trees, barriers, and road damage textures such as cracks and oil spills. The second addition in 20B is a scene builder, which imports and automatically synthesizes 3D road models from here HTLive map road data. You can visualize and edit the road models in Roadrunner, adding trees, streets, road signs, and other elements to create 3D scenes and then export them to simulator of your choice. Here I wanted to highlight some of the new capabilities of the tool. The first is the cross-section tool, which enables you to edit the shape of the road at the specified cross-sections to manipulate banking, crowning, and curb shapes. The next is the super elevation tool, which adjusts the slope and banking angle for full width of the road. While we had the ability to read here HTLive map in 20B, in 21A, we added import of additional information such as poles, barriers, and signs in the editing canvas. Roadrunner was the newest addition to our portfolio, but since 2017, as part of the automated driving toolbox, we provided tools to help you interactively and programmatically design scenes and scenarios in a cuboid environment. The image you're seeing is the cuboid environment. Here I'll go a little bit in detail in the next slides about this. As you can see here, this with a few instructions, you can create a scene, and this is all like very quick steps you can do the scenario here. And then after that, you can add actors as well as the trajectory programmatically. These instructions does that. Once, like as you know, doing programmatically has a better control of creating the scene or controlling the scene. Once you do that, you can simulate the scene very quickly. As you can see, this lines of code is simulating the scene. Some of the newest features of this cuboid environment I would like to highlight are the adding guardrails or barriers and barriers. And also you can import OpenStreetMaps into this cuboid environment scenario designer. And then you can also import Zenrin maps, which are popular in Japan. In addition, you can now specify reverse motion and also export it to OpenDrive, Open Scenario from the ASAM standards. MathWorks is a part of ASAM organization, and we are investing in OpenDrive and Open Scenario standards. We currently have some capabilities, and we continue to invest more in these areas. So far, I talked about authoring scenes using Roadrunner, and also how the driving scenario designer in ADT can be used to create scenes in a cuboid world. The simulation with cuboid world is very useful if you're developing controls, planning, tracking, and fusion. Developing detection and localization often requires 3D environment. We integrate with Unreal Engine to support these workflows as well. Some enhancements to developing with Unreal Engine include making it easier to integrate custom vehicle meshes. You can import your own vehicle mesh and work with it. And also you can control the vehicle headlights and tail lights, and you can control the weather and sun placement in these simulations. In the next slides, I'll show some of these things in a little more detail. Here, this slide, I'm going into a little bit detail of how you can control the lighting. You can see there are a lot of parameters that are supported. You can tune to simulate the lighting control of the vehicle. As you can see here, you're able to control different lights of the vehicle with specific timing control and do the simulation with those lights. And also other thing, as I mentioned, you can control the weather, and also you can control the sun and sun position as well. You can configure the rain density and all that. You can see the parameter here, which you can configure. And this reminds me one scenario which I used to be involved in, like for some of the applications we used to develop, we used to go to different places to look for the rain and then move people there and test. But whereas with a simulation, you can do all that at your desk. So this is the simulation section. With that, I would like to ask to post a second poll question here. Alberto, can you post the second poll question?
Sim. Pessoal, novamente, fica à vontade de selecionar quais são os tipos de sensores que vocês estão interessados em simular dentro de sua necessidade de veículos autônomos.
Moving on here, one of the reasons we simulate in Unreal Engine is to see the effects of the sensors. MathWorks has been shipping a variety of sensor models since 2017. Some of the sensors, for example, are radar, LiDAR, vision, lane detections. All these work in both environments. Like some of these sensors, like monocular camera, fisheye camera, work in the Unreal world only. And some of the sensors like radar track signals and IQ signals work in only cuboid world. The sensors that I talked about so far are to help detect objects, but there are also other sensors that detect the position, such as wheel encoder, GPS, IMU, and INS. These can be used in both worlds since they detect position. Radar is one of the sensors we have been investing in, and in 21A, we have a new toolbox called Radar Toolbox. The philosophy of investments in radar is guided by the different fidelities that is needed at different stages of development. For example, at the application level, engineers want to work with detections, clusters, and tracks. But if engineers were working on radar sensors, they want to look at the raw IQ signals. So we have environments and easy way to switch between these two types of outputs here. To illustrate multi-path propagation effects, we can explore shipping example which demonstrates ghost detections at both detection level and at the track level. Statistical radar models are used to generate detections or tracks in in single and multi-bound simulations. You can also generate time domain IQ signals using radar transceiver system object. We see here that the ghost target appear at a larger range than the real target, and eventually they both converge to repeat the real target. As you can see here, there are ghost targets and then real target converging together and becoming a real target. Then there are libraries available. Sorry, I think I skipped one slide here. There are libraries available to generate point cloud from a driving scenario. Using external object mesh, you can simulate LiDAR sensor data for custom meshes, and there are pre-built meshes available also. The example here shows how to record synthetic LiDAR sensor data using a 3D simulation environment. Using that, you can develop a perception algorithm using the recorded data, and after that, you can develop algorithm within the simulation environment. After that, the model records and visualizes the synthetic LiDAR data. You can use a PCP player object to visualize the streaming point clouds. Once the model has completed simulation, you can save the data to workspace and as a point cloud object. Next, you can use recorded data to develop a perception algorithm to build a 3D map of the environment. After that, we can test perception algorithm using a stress tested scenarios. This approach can be used to increase coverage for scenarios that are difficult to reproduce in the real world. There is some problem with clicking here. The camera sensor is based on the idle pinhole camera model with a lens added to represent a full camera model, including lens distortion. For camera sensor, you can specify the camera's mounting position and orientation. You have an option to choose between different mounting locations. You can also define sensor parameters such as camera intrinsics based on a pinhole camera model. And also the model includes radial and tangential lens distortion. And also you can estimate camera intrinsics and also extrinsics and also lens distortion parameters using camera calibration app from computer vision toolbox. We have examples when it comes to camera calibration. In the past, MathWorks has been providing features to calibrate pinhole and fisheye cameras. As LiDAR and camera being most common sensors in autonomous driving applications, in 20B, with newly released LiDAR toolbox, we can combine both calibration process for both camera and LiDAR to produce transformation between corresponding sensors. Features can be extracted from recorded images of the camera and LiDAR point cloud for a checkerboard to produce calibration. You can see the workflow here, how this can be performed. We also have vehicle dynamics models for 2-axle, 3-axle vehicles, and also trailers. If this is of an area of interest to you, we can have a follow-up session with experts in this area. Until so far, we have laid the foundation of MathWorks solutions to develop virtual worlds, but What we see on the field is also that how customers extend these workflows to develop new scenarios. This happens in two ways. The first method is to create new scenarios from recorded data, where customers will use the recorded data and label them and extract the information, and then create scenarios out of all that analysis. In the second method, where they create new scenarios programmatically, introducing variations into the existing scenarios. In both areas, MathWorks continues to invest to give our customers more possibilities to identify new scenarios to test. In the previous slides, I talked about simulating different sensors. Now let's take a look at labeling sensor data. We have a ground truth labeler app, which allows you to bring in camera, LiDAR, and custom data. Its primary interface is a graphical interactive tool that allows you to specify regions of interest, such as cuboids, rectangles, polygons, and also sub-labels and so on. One of the big power of this tool is to register automation algorithms. While we provide some algorithms to get you started, we often support customers to use algorithms they have developed or use state-of-the-art algorithms that are available publicly. You can, like if you have your own algorithm, you can import that algorithm and then label the scene the way you are expecting to. And here I would like to highlight some more recent enhancements for labeling. This is allowing a labeling polygon regions of interest, and then also you can label projected cuboids and to be able to synchronize. And also you can automate the labeling process with both camera and LiDAR. Basically, we are seeing very often customers wanted to use both camera and LiDAR data for ground truth labeling. Once we have the information, we often see customers programmatically varying the scenarios to generate variations out of those scenarios. Here, one example I would like to call upon is a scenario generation from recorded data, and 19A, which uses detection lists and GPS data to recreate the scenario in simulation. In 20B, we added an example for generating route variations. And we have an example to show how the Simulink can be used to program multiple vehicle behaviors existing in the same simulation. Here you can see there are different vehicle behaviors. You can configure your intelligent vehicle like velocity keeping, lane keeping, and lane change. So here we set up the multiple different tools and areas of investment in the areas of virtual worlds. This is also an area where we encourage our customers to reach out to us and work with us for their specific use cases. Basically, for example, we worked with Ford to identify important events from their logs of data. We also helped BMW in order to label vehicles and extract information from their images. And one more thing I would like to highlight is working with GM, we facilitated to recreate scenarios from recorded data and bring that into simulation in order to test their lane centering algorithms. So this is the end of the section of virtual worlds. With that, I would like to ask you to send a poll question 3 here, Alberto, please.
Só mais uma consulta rápida, né, para saber quais são os algoritmos mais relevantes para vocês, se são tomada de decisão e controle, planejamento, né, se é localização e mapa, ou classificação e detenção, e também se não for nenhum deles, pode optar por nenhum dos acima e colocar nas perguntas ou no bate-papo qual que é a sua necessidade.
I'll give 15 more seconds before we move on for the whole question. Moving on here, in the previous section, I talked about how the virtual world is going to help engineers develop automated driving applications. When we look at all these virtual worlds, we realize the need for a lot of algorithms underneath the applications to address the challenges or to develop the needed features. Basically, it requires a lot of skills across multiple disciplines in order to design such algorithms, both from functional correctness as well as the deployment standpoint. In this section, I'm going to walk through some of these in several disciplines and tools to design these type of algorithms that MathWorks provides to help engineers learn and apply them. Here, first, I'm going to focus on planning and controls as we have lengthy investments into these. Along the lines of planning and controls, we see the customers adapting our tools for various levels of automation, autonomy, and automated driving, ranging from ADAS features like adaptive cruise control, emergency braking, to higher level functions like lane change and parking. Here, I wanted to highlight some of the areas we are actively investing in. One of them is highway lane change application under planning and controls. This is an example that shipped a couple of releases back, and we continue to improve it. Some of the things we are improving are the visualization, such that you can see what's happening in the simulation and possible trajectories the vehicles may choose. The example shown here also focuses on the underlying architecture of how to build such kind of application. We have been investing in examples help you design planning for truck application, design variety of applications using reinforcement learning, including uh, parking, as well as more advanced techniques for planning in urban environments using occupancy grids. MathWorks been investing in tools to help design tracking and fusion algorithms in variety of different applications and various sensors with different data types ranging from detections, tracks to occupancy grids. One of the new examples that I would like to highlight that leverages radar sensor model that I mentioned in previous section. This example here presents how you can build a tracker which filters ghost detections from guardrails or other vehicles. In addition to visualization of the results, you can also apply metrics to both the classification and tracker, as you can see the metrics here. In addition to tracking vehicles, it is also important to track the lane boundaries, especially for lane change applications. As you change the lanes, there'll be discontinuity like this shown here. So lanes must be tracked in order to have a smooth transition, like smooth lane information fed into the electrical controller. Last example I wanted to highlight from Sensor Fusion Toolbox is on occupancy grids. This ties to planning in urban example that I talked earlier. We are seeing customers interested in creating occupancy grids. Basically, occupancy grids are going to help in very dense situations and with extended object tracking. Often these occupancy grids are created from LiDAR data, and they want to track dynamic objects in those grids in order to feed planning algorithm that can decide how to navigate through these objects. I talked about LiDAR feeding into occupancy grids. LiDAR, radar, and camera are the common sensors that we see customers use to detect and classify environments around the host vehicle. MathWorks is providing a computer vision toolbox for a while, which has been helping engineers develop computer vision algorithms that takes images as inputs. Next, I would like to focus on LiDAR Toolbox in 21A. We recently updated LiDAR Toolbox, which is originally introduced in 20B. Part of the LiDAR Toolbox focus is to help you learn design detection algorithms. Some examples we provide are detection for lanes and applying semantic segmentation and applying point pillars. These are the detection algorithms that would feed into sensor fusion, which feeds into planning and controls. Our latest investments have been in tools to develop localization algorithms. SLAM is gaining popularity from last few releases, so we have added examples for mono, stereo, and LiDAR SLAM. For higher levels of autonomy, it's important to navigate map information along with detections from camera and LiDAR. Automated driving toolbox can help you improve localization algorithms by matching traffic sense information extracted from your HT map to the ones that are detected by the onboard sensors like LiDAR and camera. This example I presented here is going to highlight those concepts. This slide here is going to give a little closer look at how the localization output or the example is going to be. As you can see, the leftmost image here is detecting the sign information from the map, as well as the right side, the middle image is showing the sign detection by the onboard sensors. In all the previous examples, we are assuming localization, or at least part of localization information, is known for planning and tracking. Localization module is an essential module for autonomous driving. More specifically, for SLAM, engineers could design and test vision SLAM and LiDAR SLAM using real data or simulated data. Sometime last year, we had worked with one customer who used orb SLAM, a type of vision SLAM. In that, we used Roadrunner to create the scenes, then converted that scene to Unreal Engine to prepare for simulation. On top of that, we added fisheye camera calibration models. Roadrunner is capable of adding different types of feature and texture to the scene, and the fisheye camera is calibrated correctly. Algorithm reacted very similar for simulated sensor data versus real camera data. So that comes to end of with this. It comes to end of multidisciplinary skills section, and the time for the last poll question number 4. Alberto, can you post poll question number 4?
Ok, mais uma consulta. Né? Quais são as opções de desenvolvimento que vocês estão trabalhando no momento? Né? Se é C, se vocês estão trabalhando com GPU, ou ROS, ou alguma aplicação como standard, né? Como AutoSAR ou DDS.
I'll give 20 more seconds to help you answer the poll.
Yes. Para quem respondeu nenhuma das acima, né, se vocês puderem colocar no bate-papo ou enviando as perguntas, qual é o seu ambiente de desenvolvimento, né, para a gente poder analisar e poder suportar vocês depois desse webinar, ok?
Okay, thank you for responding to the poll. Moving on to the next section here. So in the previous section, I talked about ways our tools help you design different algorithms and in different disciplines. One of the reason we see a lot of engineers design these, since they would like to use them as truth specification inputs to get to software. Path often we see that the customers want to go to is to take the algorithms that were developed in our tools and generate code and deploy them as software applications. For automated driving applications, most commonly our customer generate C, C++ code, GPU, CUDA code. And also we see a trend where customers generating code for service-oriented architectures like ROS, ROS 2.0, AutoSAR, and DDS. The tools are used in common software development workflows like continuous integration, automated testing, static code analysis, and ISO 26262. First, I would like to call out something in 21A, how we have integrated vision detector into Simulink and generate C++ or GPU code. GPU code generation is performed from Simulink. This is a nice example which allows you to collect metrics on how vision detector is doing, but also through software in the loop, we can measure execution time and make performance improvements across different variants of the code generation. As you can see, the different variants of the code generation here metrics. In addition to generating code for vehicle detections, we also provide new examples to help you learn how to generate code for lane detections, controls, and planning algorithms. In each of these examples, we can also learn how to run software in loop simulation and review code metrics like coverage and execution time. In the previous example, we focused on algorithm code. Often we see the need to integrate those algorithms into service-oriented architectures like ROS 2.0. This example here shows how to generate ROS nodes in the context of a parking valet application. The last example that I would like to highlight is ISO 26262. Engineers have been using MathWorks tools for IS 26262 development of decisions and controls for a long time. One of the things we heard from customers is that they would like to see an example which would walk them through on how to apply it in the development of automated driving applications. This is of our first revision of IEC certificate for ISO 26262. If you are working on safety critical applications or standards like ISO 26262, this example could help you get started. We also have additional capabilities and services available to offer in order to make you successful in this area. Up until now, I talked about different tools for developing algorithms and techniques. For code generation, we can see here how our customers are using our tools. This is an example of Hitachi developing their adaptive cruise control system, and they are happy with the quality of the generated code. Another example is from last year's MathWorks Automotive Conference presented by AVL. AVL used Simulink to design controls and planner for highway lane change. Manda also presented something similar in the Mac. One more user story here is that I would like to mention about is Electrobit, where they developed driver monitoring system using adaptive AutoSAR. They commented that their development time got reduced from a year to 3 months in this case. MathWorks can partner with you in your development if you are into these kind of use cases and need support in the space for prototyping or for deployment purposes. So this is the end of the presentation, and I think we have 10 more minutes left. We can try to answer the questions you may have. You can ask the questions directly or through the chat window. Alberto, you see any questions to answer here? Or?
Alguma pergunta? Vocês podem fazer a pergunta em português ou em inglês, o que se sentirem mais à vontade.
People are a little bit shy, probably.
Okay.
Pessoal, se tiverem questões, dúvidas, tenha a dúvida sobre o sistema de desenvolvimento que vocês estão aplicando. Algumas pessoas colocaram nenhuma, né, entre o C, o ROS e a GPU. Né, nós estamos interessados em auxiliá-los, puder questionar sobre o suporte que você precisa para o seu desenvolvimento, fique à vontade. Pode mandar pergunta também, abrir o microfone e falar em português também, eu faço esse meio de campo para vocês poderem endereçar a sua questão. I suppose that no questions for now, Naveen.
Okay. Yeah. Like if there are any questions, I can answer through the email also in the later time. Probably we can end the webinar then.
Yes. Pessoal, novamente, muito obrigado pelo tempo de vocês. Se ficou alguma dúvida ou tem alguma necessidade especial, vocês podem entrar em contato diretamente com o OPENCADD. O Naveen também direcionou o e-mail dele. Né? Muito obrigado pelo tempo de vocês. Thank you, Naveen, for your presentation and time. See you next time.
Thank you guys for arranging this, and thank you for all the attendees for listening. Bye for now.
Bye-bye, guys.